In the speaker situation set up.
Microphone.
The speaker, we don't know if this one's working, so we want to make sure that the only people can hear us.
Okay. Although it says it's connected.
Hi, Gretchen, can you hear me again?
Well, Mike is loud and clear, and you
Yeah.
are
My
from a
system is not,
distance.
for some reason, is not connecting it to, so this is all going through my
Okay.
laptop,
Do
and
you
it.
want me to try on the microphone on my laptop?
Yeah, let's try that instead.
Yeah. Hi, Gretchen, can
That's much better.
okay. Yeah.
Okay.
Much better.
I will mute it here then.
Yeah, okay.
Okay. Thank you. Okay.
So, are we good?
I think so, yeah.
Zoom people can hear?
I think so. And
Going through her mic.
Yeah.
We don't know if this is working or not.
Zoom people? Is this working?
It's much,
I
that,
think
Marta,
they can
that's
hear us, yeah.
fine.
Okay, great.
And if not, please complain.
But they cannot hear them, right? That's the thing.
No,
They can.
Well,
no.
So,
Mike, you'll keep an eye for any
Keep an
questions.
eye.
Yeah.
Online?
Yeah.
Great. Well, I am so thrilled. We've made a standing room only situation for Marta. I'm really pleased that you came. Marta is a national fellow at McMaster, which we were just saying, so close, but so far away when you got in the car. I'm really glad you made it here. Prior to being at McMaster, she was in her PhD at Heidelberg, working with Richard Preussen. And this is gonna be great. So, and she welcomes questions during the talk, and I just think it's always nice to say your name before you ask your question.
So, hi everyone. First of all, thank you so much for inviting me here. If I'm not loud enough, please let me know, especially the online people. If I'm not clear enough, please do let me know. So I'm Marta, I'm at McMaster. I'm interested on stellar clusters from small scales, how they form, how they evolve, but also their connection with galaxies. I normally study stellar clusters using numerical simulations of galaxy formation, and today I want to talk about a project that started as a side project, just a fun summer, just a fun idea to do over a summer, and has been taking sort of more and more time.
Can I interrupt a second?
Although my theories, I'm gonna pretend to
I'm
be
hearing a
more
lot
clever.
of background noise.
The project is on how we can try and trace the Dharma Tehelo using diffuse stellar light and globular clusters. And this is not an idea that we're suggesting, it's actually been suggested many times before, but I wanna describe what we've been learning using the results from the E-MOSAICS simulations. So for my talk today, if this a second, okay. So for my talk today, I want to start with what are globular clusters, what are their properties, where are in galaxies, where do we see them, and how do globular cluster systems and diffuse stellar light sort of assembles in galactic systems. Then I'll describe how we can model sort of a brief overview of how do we model stellar clusters in numerical simulations of galaxy formation, what assumptions and what caveats do we have to make to be able to study this. And then I'll jump onto how can we constrain Dharma Tehelos using stars and globular clusters using the numerical data. So I like to start with this quote from William Herschel's catalog. This is one of the first catalogs of star clusters and planetary nebulae that are known of, and they write in their catalog what they think is their idea of a stellar cluster. And I'm quoting here, they say that, but first of all, it will be necessary to explain what is our idea of a cluster of stars, and by what means we have obtained it. For instance, I shall take the phenomenon which presents itself in many clusters. It is that of a number of lucid spots of equal luster scattered over a circular space. in such a manner as to appear gradually more compressed towards the middle, and which compression in the clusters to which I allude is generally carried so far as by imperceptible degrees to end in a luminous center of a resolvable blaze of light. These are just two examples of the type of objects that William Herschel and his sisters were observing, and you can see that they correspond to extremely dense stellar systems. We now know that these objects are gravitationally bound groups of stars, and they have a set of properties that make them quite peculiar. So globular clusters are typically defined to be massive and bright. They typically have masses above 10 to the 5 solar masses. They're old stellar populations, so they have ages comparable to the age of the universe. That means for us at least older than 10 gigayears. They tend to be relatively metal poor. They're quite compact, so their half mass radii is of the order of 3 parsecs. And because there are so many stars in such a small region, they're expected to correspond to single stellar populations that formed all at once. However, when we look at the chemical abundances of the stars within these globular clusters, we see that there are some spreads in some of the elements. And this is indicating that there might have been some enrichment process and several bursts of star formation within them. So all of these properties make them quite peculiar, and they are quite interesting objects to study. William Herschel was observing globular clusters in the Milky Way, and when we consider what he was looking, this is a picture of the Milky Way from the early data release 3 from Gaia. This is a number density image, so every pixel corresponds to the number of stars, and so brighter pixels means more stars. We're seeing here the galactic plane with all the dust, and then the small and the large Magellanic clouds, and you can see that there's some very bright spots sort of scattered around within the galaxy, and these are all these globular clusters that we were describing. So just to give you a bit of an idea, these very bright spots correspond to these dense and massive gravitationally bound stellar systems that I was describing earlier. In a galaxy like the Milky Way, we expect to have between 100 to 200 globular clusters. It depends a bit on your definition, but this gives you an idea how in our own galaxy, there's many of these systems. William Herschel had a lot to look at. To give you a bit of an idea of how different these objects are compared to galaxies, I mentioned that the mass of globular clusters is of the order of 10 to the 5 solar masses, whereas the mass of the Milky Way is of the order of 5 times 10 to the 10 in stellar mass, of the order of 10 to the 12 for total halo mass. So these are 7 orders of magnitude. So when later on I'm going to be describing how can we model globular clusters together with their galaxy, you can already see that we're trying to cover a wide range of scales. So we're going to have to be making some caveats and some assumptions to be able to model all of these at once. This is in terms of their masses, but when we compare their sort of spatial scales, globular clusters are smaller than 10 parsecs for sure. Whereas the sizes of galaxies are of the order of 20 kiloparsecs. So again, these showcases that we have to study wide ranges of scales when we're trying to model these two things together. Globular clusters have been seen not just in the Milky Way, but actually they've been found virtually everywhere. So this is a composite image that's showing the total mass in globular cluster that a galaxy holds as a function of the halo mass, the host halo mass of that galaxy. And this is the result of combining 2 images from 2 different papers that cover a very wide range in halo masses. So we're going from the dwarf regime here in the left towards galaxy cluster regime. So just as an example, this is where 4 different galactic systems lie. So the small Magellanic clouds, our own galaxy, and the Fornax and the Virgo clusters. What we've been seeing when observing globular cluster populations is that we find them virtually everywhere. So basically, if we find a galaxy, that galaxy is going to have globular clusters. And the properties of the globular cluster population seem to correlate with the mass of the galaxy. So more massive galaxies have more globular clusters, and the overall globular cluster population is going to be more massive. The only place where this rule seems to break is in the dwarf regime, just because these galaxies are so low mass that they might not even have enough mass to form one globular cluster. But this is very interesting because it means that if we want to use globular clusters to trace their host galactic environment, we find them everywhere. So they're good tracers. Now, these. Now, why do these galactic environments have so many globular clusters? Is it because they form there, or is it because they come from somewhere? When we examine how galaxies grow in our current lambda CDM framework, we think that galaxies grow via a combination of in situ star formation and accretion of smaller satellites. This is an image that's coming from the illustrious DMG simulations that is showing what is the mass fraction of stars that's coming from accreted satellite galaxies as a function of the halo mass of that galaxy. And there are several lines represented. What they're seeing in simulations, and this is a result that's coming not just from the illustrious TNG collaboration, but has been seen in many different models as well, is that when you are looking at the material that is in the outskirts, that material is predominantly accreted regardless of the mass that you're considering. When you are looking at the material that is within 30 kiloparsecs, so what you would consider to be the central galaxy of the halo, the fraction of stellar mass that is coming from accreted galaxies increases strongly with the mass of the halo. And this is indicating that more massive galaxies will preferentially via the accretion of several smaller satellites rather than by in situ star formation. So the globular cluster populations that I was describing earlier are the composite of smaller globular cluster populations that have been assembled over time. And what's quite interesting as well that they're seeing in this work is that when they're considering the central galaxy and the intracluster light, so this is the diffuse light that are free floating stars that are not bound to any galaxy, but sort of bound to the entire halo, they see that the accreted fraction is actually higher. And what this is indicating is that this diffuse light that we see permeating the space between galaxies and galaxy clusters is made up of accreted material. And this is very interesting because it means that we can use this intracluster light or the globular cluster populations that we see filling up the space in galaxy clusters as a relics of the formation process of their host halo. So these are just two different examples. We're looking.
Sorry, can we go back?
Say your name.
Yes, my name is Niayesh. So could you explain what is exactly the definition of the y-axis here?
So these are, my understanding is that these are stars that in the simulation did not form in what ends up being the central galaxy, but is formed somewhere else and then ends up in central galaxy. So you can think of it as they run the simulation, they get the redshift 0, so the final snapshot. They look at all the stars that are in the galaxy and they say, were you born in this galaxy or not?
Doesn't matter where in that galaxy, just within the.
Within the galaxy.
Within
Yeah.
that galaxy.
So you go back in time and you find the corresponding central galaxy in all the previous snapshots, and you ask the question, were you born in that object or somewhere else? That's typically the definition for these things. But then there's some ambiguity because in simulations, we don't have a continuous story, we just have snapshots. So what happens if you form in between snapshots or if you form while a galaxy is accreting? That's a bit tricky, but that's generally the definition.
Is the color the amount of distance they have traveled?
No, the color is different selection for the stars. So you have your galaxy, you have your halo, and then you're saying, okay, am I looking at all the stars that are within 10 kiloparsecs in my galaxy? So just to the east, that would be this gray line. Am I looking at everything within 30 kiloparsecs? So you would be encompassing the stellar halo. Am I looking at everything that's outside 100 kiloparsecs? So very much the outskirts of the galaxy. Am I looking at the central galaxy? And so the idea is that depending on which selection you're making, you might be looking at more or less amount of accreted material. But yeah, it's quite interesting to see that even if you're just looking at the inner 10 kiloparsecs of the galaxy, the amount of accreted material is increasing. So this is telling you that when a galaxy is accreted, it's not only deposited in the outskirts of the halo, it can also travel all the way through to the galaxy peaks. So if you're trying to distinguish between in situ and accreted and you're saying, oh, everything in the disk is in situ, that might be wrong. Yeah, so these are two different examples, two different observational examples of intracluster light and intracluster globular clusters. I'm very much not a fan of this name. So the image on the left corresponds to diffuse stellar light of SMARS 0723 taken with the Webb Space Telescope. You can see this between BCG of the galaxy cluster, and then there's a number, and then there's all of the galaxies, but there's a number of features. What the authors have done is that they have identified what they call iso contours. So these are the structures that are defined by pixels of a given stellar surface brightness. And you can see that there are some features in the lab. So there's this feature here, there seems to be this loop here that has several galaxies. So what the authors are suggesting in this paper, and has been suggested before, is that using, or we can observe the diffuse stellar light that's permeating galaxy clusters, and as a way to reconstruct what has been the assembly history of their host halo. And interestingly, we can also do the same thing, or we seem to be able to do the same thing with globular clusters. In this paper, they derived and spectroscopically confirmed sample of intracluster globular clusters in the Fornax cluster, and these correspond to all of these colored dots. And you can see here that their globular clusters are nicely associated with these black lines, which are features that come from the diffuse light. So they are suggesting that we can also use these globular clusters as tracers of what has been the assembly history of the host halo. But I mentioned that I was interested on not just tracing what has been the assembly history, but actually on trying to observe dark matter halos. Probably everyone in the room is aware that galaxies are not just made up of stars and bees, they also have globular clusters, there's some satellite galaxies, there's a stellar halo, and everything is embedded within a larger scale dark matter structure. However, when we try to observe it with electromagnetic telescopes or observatories, we do not see dark matter because it doesn't radiate, so we cannot see. So if we want to trace the dark matter structure, we need to use the gravitational interaction. So typically, and this is work that many of you do in the room, we use gravitational lensing or X-ray emission to try to trace this dark matter halo. And today I want to show how we might have another way of tracing it, which is using the stellar light, so the diffuse component of the stars that are created and the globular cluster populations. And just to show that this is not an idea that I sort of suggested for the first time, it has actually been done in the literature before, but it has been done using observations, which is very impressive because it's extremely challenging. So I'm going to show 4 different examples of studies that have tried to do this. In these different examples, they're focusing on one object at a time. So in this first one, they are doing very deep HST images of a Bell 1689, and they're showing the globular cluster number density map, the distribution of galaxies with the diffuse light, the total mass distribution from gravitational lensing, and the X-ray emission. And what they're seeing is that there is a structure in the total mass distribution that is not seen in the X-rays, but it is seen in the galactic and the stellar light maps, and also in the globular clusters. So this is for a Bell 1689. It has also been done for a Bell 2744. So this is the globular cluster number density map, and this is the total mass model. And you can see that there's this sort of elongated banana shape that we also see here. They also did very deep HST images, and despite these being very deep, they actually only cover the tip of the globular cluster mass function. So they're only seeing the extremely bright objects, and they're trying to interpolate and try to say what the overall population is doing. But it's very challenging because it's quite far away. For Abel 2744, there's also this study where they're not looking at the globular, they're considering what the intracluster light is looking and comparing it with the mass distribution from gravitational lensing, and comparing it also with X-ray emission from Chandra. And you can see that for this particular galaxy cluster, the banana shape that we were seeing is only seen in the ICL, but it's not seen in the X-ray emission. So they're suggesting that the diffuse light might be a better tracer of the total mass distribution than the X-rays. What's interesting of this work is that they not only focus on Abel 2744, but they include 5 more clusters, and these seem to be a signature across all of the different environments. And lastly, lately there was this very interesting paper where they're comparing the intercluster light as the background of this image. The globular cluster number density contours are these blue lines, which are a bit difficult to see, and a lensing model for SMAX 0723, which are these yellow lines. And all of these was observed with James Webb, so these are deeper images. And they're also suggesting that there is a correlation between the lensing model and the globular cluster contours here in the blue. And you can also sort of see it in the stellar light. So all of these observations taken together are indicating that we seem to be able to use the diffuse stellar light and the globular cluster populations in galaxy clusters to try and correlate with the total mass distribution, and this seems to work better than X-rays. Now the question is why?
It's Nyash again. So, actually, should I say it every time I did it?
I think it creates a friendlier atmosphere,
Yeah.
not the stranger, is what I'm
That's
saying.
good, yeah.
It also creates an element of humor.
So, I mean, this is, the visual comparison is all good, but I mean, would it be better to do like a cross-correlation coefficient to
Yeah.
see which one is actually
Yes.
better?
Yeah. So that's actually something I'm gonna try and get to,
Okay.
if you give me.
Okay.
So I'm gonna say the work that did the ICL, so they did the visual comparison, and then they also used a metric to compare how closely they are. We use the same metric, so I'll talk about that in a second.
Okay, so another question, just more of a clarification. When you say X-rays, it could come from X-ray binaries or it could come from hot gas. So which X-rays are we talking about?
Hot gas, I
Okay.
think that's it.
Okay.
Yeah, so this is what we're learning from observations. Now, the question is why? Why, first of all, why are the stars and globulars tracing the total mass distribution? Can we only do this in galaxy clusters, or can we extend this analysis to lower mass galaxies? And as Nyash was saying, how good is this agreement? So in order to answer these questions, I resorted to using numerical simulation. So just as a brief overview, how can we model star clusters and their host galaxies in simulations? So our current understanding for star clusters, which is debatable depending on who you ask, is that once upon a time, the universe was very gas-rich. And in these gas-rich environments, there was stellar cluster formation in these very dense gas clouds within the galaxy. And the combination of the high merger rates that happen at high redshift together with the feedback from these stellar clusters means that stellar clusters can migrate from their natal gas-rich environments towards the outskirts of the galaxies and even towards the halo. And this is critical because within the natal gas-rich environments, there are tidal interactions with passing clouds that inject kinetic energy into the stars of the clusters. This is what, if this happens quickly enough, this is considered to be a tidal shock, and this can quickly disrupt stellar clusters. So it's critical for them to leave their natal environments towards the outskirts. Because in the outskirts, the main disruption mechanism that stellar clusters have are just two-body relaxation. So just the kinetic exchange between binaries or between stars in the cluster can mean that some of them leave it. But the time scale associated with this disruption mechanism is much longer than this one. So clusters being able to leave their natal gas clouds is kind of critical for them to survive. Now, we have to remember that stellar clusters are embedded within galaxies, and as all of you know, galaxies are embedded within a larger scale environment. So if we want to model how stellar cluster formation and evolution happens from high redshift down to redshift 0, we have to be able to model from the starbursting environments where stellar clusters form, that in the tiny galaxies, what we see in the local universe, down to more quiescent environments where we see more evolved cluster populations. And we want to be able to model the galaxy. So we want a realistic galaxy population at the same time that we want a realistic stellar cluster population. So what we've done, or one of the projects that we've been working on in order to solve this conundrum, is coupling a subgrid description for stellar cluster formation and evolution with the Eagle galaxy formation model. So These combination of models allows us to study from the larger scale environments where galaxies are forming in the nodes of these down to one node, one galaxy, and the stellar cluster population within these galaxies. For this particular project, we're using the Eagle high resolution model. We have a volume limited sample of 25 cosmological zoom-ins of Milky Way mass galaxies, but we have also run a periodic volume that has a size of 34 megaparsecs. And this allows us to study from galaxies that have, I think it's of the order of 10 to the 7 solar masses up to a smallish galaxy cluster of 10 to the 13 solar masses. And this is the periodic volume that I'm going to be using for the results later on. So I've mentioned that we're modeling stellar clusters using a subgrid description. What does that mean, really? So in the simulations, what we're doing is that every time that a gas particle forms a star, we paint some clusters onto the star. How do we paint these clusters is based on models that reproduce the properties of young massive clusters in the local universe. And as the star is sort of living through the simulation, these stellar clusters are losing some mass. And how these clusters are losing mass is tuned to simulations to embody simulations of clusters. So each star particle in our simulation may host several stellar clusters, each of them described with a mass, a size, and undergoing a certain amount of mass loss, as well as metallicity. This is where we have to be careful when we're interpreting sometimes the results, because the input models that we use for the simulations might influence the results. But we've been hopefully been quite thorough at making sure that what we're putting in is not what we're getting out. Okay.
Isn't it true that all the stars form in a cluster?
Yeah, so I mean, so stellar clusters is the idea that they're gravitationally bound.
Right.
I would say no. There can be some stars that form in isolation, or that's a problem. It's also okay. There's a time scale issue. When do you define that a stellar cluster has formed and is bound? Because what can happen is that at the beginning you might have 2 or 3 stars forming. They might be bound. Is that a binary? Is that a multiple system? Is that a cluster? If you have a few more stars that are sort of bound to each other, but they quickly dissolve, have they been a cluster? Or it's a bit complicated. I would say no, but it depends on who you ask.
Well, I guess this the question would be that is it that like there the spectrum of sizes that range from, I don't know, 10 stars to 10 to the 5 stars in a cluster, or is it really like a dichotomy, like like big clusters and the small clusters? And I guess it's not clear to me.
So there's the mass function is, well, we think it's continuous. So it takes the distribution of masses that clusters have when they're forming. What we observe is that it seems to be a power law of the slope of -2. So it decreases towards higher masses, and then it seems to have an exponential cutoff. This is normally measured down to masses of 1,000 solar masses, because it gets very difficult to observe towards lower masses.
And is that what you're using here?
Yes.
Okay.
So for our simulations, for the masses that we spawn, that we assume a power law of slope of -2 with a certain exponential cutoff. Yes. Yeah.
Can you repeat? You just said it, but I think I missed it. You said once a star forms, every single star you promote it as a stellar cluster?
It depends. So what we do is depending on what were the conditions of the gas particle from which this star formed, it gives us a cluster formation efficiency. So what is the likelihood that this star is going to form clusters? This efficiency is higher in higher gas pressure environments. So if your star is forming from an environment that has high gas pressure, you are assuming that it's more likely to form stellar clusters. Whereas if it's not, then it's not going to have any. Okay. So when we look at our star particles, some of them have 3 clusters, some of them have none. it depends from where they fall. But they can all spawn them. It just depends on the environment.
So if you have an environment where there's a probable case, then you associate the mass in that environment.
Then we associate part of the mass of the star to that cluster. Yes.
It doesn't mean you do, like, there's no mass loss or something, the mass is the same, conservation of mass is the
Yeah,
same.
actually, yeah. So we don't. Yeah. So the global mass is conserved because whatever mass was in the gas particle is in the star. Now, these stars in these simulations have 2 × 10⁵ solar masses, whereas we have clusters that are more massive than that. So what we do is that the mass that we use for gravity, the mass that we use for stellar cycle, is the mass of the star. Under the hood of the star, stellar clusters can be more massive, but because they do not affect the simulation, it's fine. So locally, that mass is not conserved, but globally, because there are stars that have no clusters, it is. So this is a trick that sometimes is played with subgrid physics, just because you need, or you're trying to model something under the hood. So as long as the properties of whatever you're modeling doesn't affect back the simulation, it's all right. That's why I said you have to be careful sometimes when you're interpreting simulations, because you have to make assumptions in order to solve these questions. Yeah. So when we put all of these models together, this is what we can do. This is a movie that's showing the formation and assembly of one of our Milky Way mass galaxies. The gray color bar corresponds to the gas density, and all the colored dots that are running around are stellar clusters that are forming. So you can see how the main galaxy is forming here, and it's assembling through a combination of in-situ star formation, but also fusion of stars. So by redshift 0, or at the present day, when we look at the globular cluster population that this galaxy is going to have, going to be a composite of all of these smaller satellites coming in. And we can do this type of study, we can do it over sort of cosmic time, so over 13 years. So I'm going to jump now on how, using the results from these numerical simulations, we can try and see whether we can constrain the dramatic halos using light and globulars. The first thing that we need to do is, so I'm using the numerical simulations. In particular, I'm using what I mentioned is the periodic volume that has 34 megaparsecs on the side. These give us a wide range of masses of galactic environments to explore. And for this particular project, I've been looking at all the dramatic halos that host central galaxies more massive than 10 to the 10. The idea was to explore whether we can trace the dramatic halo of galaxies like our own, which is 5 times 10 to the 10. So the first thing that we need to do when we take the simulations is kind of put on my observer hat and say, okay, I'm no longer going to work with physical quantities, but I need to create mock images, which was very challenging. So what you're seeing here on the left is the dark matter surface density for the most massive halo in our galaxy, which is the one that I'm going to be using as an example. You can see that it has a central BCG, and there's also very massive satellite here, and there are also some sort of each of these dots are sort of subhalos and galaxies. Now for the stars, I created stellar surface brightness images using the SDSS R-band, which you can see here. Again, we're seeing the central galaxy, there's this massive satellite, and there's all of these diffuse light sort of in between the galaxy clusters. And for the globular clusters, I converted their masses to absolute magnitudes. I made a magnitude cut, also a color cut, just to be able to sort of mimic what observational surveys typically do. And this is the globular cluster number surface density. And again, you can see the globular cluster population that would be associated with this galaxy, the one associated to the massive satellite, and all the other ones that are associated to the other galaxies. Now, if we're trying to identify structures here, it's very difficult because of the point source nature of globular clusters. It's very difficult when it's very messy when you're trying to look at structures here because it's very noisy. So the first thing we need to do is we need to smooth the images, which is not showing. Oh, yeah. So the first thing we need to do is we need to smooth the images, and then we can try and look for structures. So what we're gonna try and do here is as whether using these sort of observational tracers, we can find any correlation with the matter distribution. To identify these structures. So these color lines that are being shown in the image, what we're doing is that for each image, we're measuring the radial profile, and at given radial distances, we're interpolating the density at that radii. And then we're drawing contours joining all the pixels that have that density. The idea is that if the distribution were to be perfectly spherical, you would just end up with perfect circles at given radii, right? But because the distributions are not spherical, you're seeing the density at a given radii. So what we can see already, just for sort of from a quick look, is that these Darmata halos seem to be elongated. There's the central, there's the satellite. We see the same in the star, there's the central, there's the satellite, and the same for the globular clusters. So some level of agreement seems to be there. We already knew these from observations, but how close is that agreement? One of the things that we need to do that is a bit challenging is that at each radii that we're considering and that we're drawing the contours, you can see that there are several lines of the same color. We have to choose one in order to make the comparison. So what we do is that we choose the longest contour. Whenever there are special cases like in this one, where you have very prominent galaxies one next to the other, it can happen that in each map, you're looking at different galaxies. So for example, here you're looking at the satellite, here you end up looking at the central, here you look at the satellite. Luckily, this only happens in like a very small number of our halos, so having satellites in the images doesn't seem to affect the method at all. So when we choose each of our structures, each of the different radii, we can compare them. This is a messy image, but here you're looking at the same galaxy, and now the contours for each component for each population is with a different color. So globular clusters. So if you're looking at globular clusters, and at an inner radii, you're seeing the satellite. At an outer radii, you're seeing the central. At an even outer radii, you're seeing the satellite again, and then sort of join. Whereas for the stars, that's the other way. Luckily, this only happens in a very small number of cases. But we, as you were asking earlier, we can quantify this agreement between the contours. So this is done with a metric that's called the modified Hausdorff distance, and it gives you the average distance between two contours. So again, if you have two perfect circles that are separated by a given distance, that's going to be the distance that this metric is measuring. As another example of one of our other halos, this is what most of our halos look like. So the previous one was very messy because it was a major merger that was currently ongoing at vertex 0. Whereas most of our halos look like this. You have a very massive satellite in the center. The distribution is almost spherical, and by looking both at the globular and the star, you're fairly close to the dark matter distribution. So we can.
So how do you know which contour you want to compare to which contour? There are lots of contours, right?
Yeah, so what we're doing is we choose two distances. So I think we draw 7 here, and we just choose 2. So at 5% of R200 and 20% R200, just because we have to choose. So we say at 5% R200, this corresponds to this distance, this red contour here, and all the other ones that are underneath it. So what is the comparison between globular clusters and dark matter, globular stars and dark matter, and so on? And then add 20%, what is the distance between these two pairs?
So you match the highest density of the two maps to be the center, and then you go.
No, the maps are centered on the most massive galaxy.
So it could be that the center of the two contours only.
Yes, so that's a problem. That's a problem with the previous image, where what you're seeing in each of your tracers does not correspond. That's what I was trying to say here. It's that you are seeing the other galaxy. But this only happens when you have two very massive satellites with one next to each other. So like when you have like a major merger ongoing. In our sample, which is like almost 120 halos, this only happened, I think, twice. So it depends a bit on your sample. It's not too bad. So here's what I want. So now we're measuring this modified Hausdorff distance, which is giving us what is the kind of average distance between two contours. We're normalizing it with R200, just because we're comparing halos of different masses, and otherwise it would be a bit of a mess. And we're comparing contours that are drawn at two different radii, 5% R200 and 20% R200. The idea is to say, okay, this is the inner part of the halo, this is more or less towards the outskirts of what we can normally see. And then symbols correspond to different pairs. So we're using stars to trace our mother, we're using globular clusters to trace our mother, and we're using globular clusters to trace stars, just to see how close they are one to another. And these symbols here correspond to the median with some percentile. So this is just a summary of all the points there. What we're saying is that when we're considering just the inner part of the halo, globular clusters seem to be closer to the dark matter distributions than stars, because we can see that these orange points, and it's lower than the blue one, also within the error bars. But if we're going outwards, towards the outskirts, stars seem to be closer than the dark matter, although the scatter is larger. So this needs to be taken with a pinch of salt.
Sorry.
Tell me.
Oh yeah, sorry, Neil. Like this choice, I mean, so this number must depend on like the smoothing that you apply to make your contours, right? But this, it's hard to interpret, I guess, this number. So I'm just wondering how come you don't do, the thing that, Naya suggested, which is just compute the cross correlation correlation.
So we computed the correlation coefficient between the images.
Yeah.
It's the Pearson one, and yeah, there's agreement. We wanted to have an estimate of saying, let's say that in observations you can draw the same isodensity contour of globular clusters. How far away is the one for dark matter, right? If you're just doing the, so if I might draw, so you have your image. So what I had in mind, at least when I was starting the project, is say this is the contour, this is the structure that my globular clusters are sort of encompassing. Could I say that the dark matter is sort of within this, right? So this gives me an idea of what is the shape of the dark matter halo. So we calculate the correlation coefficient between pairs of images. We see that it's higher. There's statistically correlated the structures that we see. The smoothing that we apply on the images is about the size of the effective radii of the main galaxy. So it's 2% R200. And we tested this. The idea is that this is large enough that is smoothing out all the small scale noise that you get from the point source distribution of globular clusters, but not large enough that you're erasing all everything within your image. And the other thing is that the radii at which we're measuring the contours are larger than the size of the kernel that we're using to smooth the images. So in principle, you shouldn't be affected by this.
That isn't obvious, but okay.
Okay, I can show you I have some comparison images, but I didn't put them in the slides that I can show you later if you're interested. So yeah, so one of the things we were saying when we were choosing how to smooth the images was that if it was too small, you had too much noise. If you were too large, you erased everything. So you erased any signal that you might have. So that's what.
Which is why the cross correlation coefficient as a function of radius, I think, would just tell you.
Might have been, yeah, might have been. I mean, yeah. Sometimes you just don't think of these ideas when you're doing the project, but yeah. Yeah. So.
Still smooth it out, or do you want to do the point?
Yeah.
So it's a function of the, of the pair separation, right?
But the mass of the dark matter on the.
I guess you could do the cross correlation between the centers of the distributions.
I think there would be a smoothing there as well, but yeah.
No, so for example, right, so you can do the cross spectrum compared to the auto spectra as a function of rate. I mean, that's a function of scale, right?
Yeah.
Or, as a function of scale, you can figure out.
Okay.
Anyway, yeah.
Yeah, I think I'm not familiar enough with these metrics, but I'd be interested to take a look, because this is something I find it very interesting. So another question is, why are stars and globulars overall tracing, and why is there agreement? There's some better agreement at some radial distances than others. So in order to answer that, I decided to look at the fraction of objects that are accreted, so either stars or globular clusters versus in situ. the function of projected radius, so the radial profile of the radial expansion for galaxies of different masses. These are low mass, and it's Milky Way, and then higher mass galaxies. What these vertical lines are the two radial distances that we're comparing the contours of. And what we're saying is that in low mass galaxies, so Milky Way, because these ones in situ star formation is still a predominant mechanism to assemble most of the mass of the galaxy. The fraction of accreted globular clusters and in situ globular clusters in the inner halo is very similar and the same for stars. So for low mass galaxies, the accreted component doesn't have enough predominance. So you cannot really trace, or there's a bit of a scatter when you're tracing the distribution. But as you go towards more massive galaxies, because these two means build up preferentially via accretion, the accreted fractions are always higher than your in situ fractions at the radii that we're considering, and it is this accreted material that has come into the gravitational potential and have had to settle into the potential, the one that holds the signal about what is the total mass distribution. So that's why we can use the stars and globulars to trace it. One of the things that we wanted to, but one of the things we wanted to do with this project is because we're using simulations, we can mock our images in many different ways. We had to make a choice on what was the stellar surface brightness that we were using as our fiducial, but we wanted to test how the results change if we use different values for sort of current and sort of upcoming observation. So for the same halo that I was showing before, these are our fiducial maps. This corresponds to the SDSS stellar surface brightness limits, Euclid, and Vera-Rubin. And you can see that by sort of lowering or going towards deeper and deeper stellar images, we're adding information in the outskirts of this halo. And so when we're then doing the comparison with the dark matter maps, we can carry on the comparison to outer and outer radii, but we're actually not improving our current measurements. So if we're interested in looking at the mass distribution within the inner halo and even up to 20% or 200, our fiducial values were good enough. For the globular cluster populations, we did a similar analysis where what we changed was the absolute magnitude that we were applying to the globular cluster population. So what we used as a fiducial is say, okay, we want to observe all globular clusters that are at least as bright as the peak of the globular cluster mass function. What happens if we go one magnitude higher? What happens if we go one magnitude lower and even two magnitudes lower? In this case, we're not adding information in the outskirts. I mean, we are some of it, but we're adding a lot of information within the galaxies itself. So the actual value, the agreement with the dark matter maps was improving a lot. So when we're observing fainter and fainter globular cluster populations, we can extend the comparison with the dark matter distribution to lower mass galaxies further out, but there also, we can do it a bit more actively. So this is a push for, we should be observing fainter globular cluster populations. Something that came up sort of towards the end of this analysis was the idea that we have these images, these components, all of them have a radial profile, and was the question of whether we can use the radial profile of stars and globular clusters to trace the radial profile of the dark matter halo. So what we did was we're looking at the ratio of the stellar to dark matter mass surface density and the globular cluster to dark matter surface densities. These gray lines correspond to the most massive halos within our sample. We did the same analysis for the two beings with lower masses, but I just decided not to include them here. The orange and the green lines correspond to the median and a linear speed performed in the simulations, whereas this purple line corresponds to the measurements for Abel 1689, and the red line is a relation that was found in the cluster eagle simulations. What we're saying is that by doing accurate measurements of the radial profiles of stellar surface brightness or stellar mass density and globular cluster surface density, there is a linear fit to the dark matter profile. So if we have measurements on the stars and the globular clusters, we can make predictions of what the dark matter mass profile is going to look like. And what I find very interesting is that this slope of the relation is getting shallower as you're going towards more massive halos. So Abel 1689 is of the order of 10 to the 15 solar masses, whereas our most massive halo is of the order of 10 to the 13. And we do see that the slope of the feed is getting shallower. And this is because more massive halos build up preferentially via accretion. This accreted material is being deposited preferentially towards the outskirts of the halo, and so you have more stuff here, and so you are ending up with a shallower profile. And the last thing that we looked at was we characterized the spatial distribution of dark matter stars and globular clusters with ellipses. And by looking at what is the semi-major axis of those ellipses, you can look at what is called the misalignment angle, which is what is the angle between the semi-major axis of two different distributions. The idea is that if two distributions are aligned, they should be sitting one on top of the other. We looked at pairs of globular clusters and dark matter, globular clusters and stars, and then stars and dark matter for the two radial distances that we're considering. And we saw that overall, globular clusters and stars seem to be kind of within 10 degrees away of dark matter. So by doing deep observations of stars and globular clusters, we seem to be able to recover the shape, the profile, and the orientation of dark matter halos for galaxies down to 10 to the 10 solar masses, which is quite exciting because that's sort of where the Milky Way lies. Before ending, if I have a bit of time, I just want to finish by saying that this is a very exciting method because this seems to be opening a new way of tracing dark matter halos, just using stars and globulars, but there are a few caveats. So the first one is, in order to do this, we need deep stellar photometry over wide areas, and these can be very affected by galactic cirri. There is a push, I know there's a push within the Rubin to try to overcome this through the pipeline, and I think similar analysis or this is being taken care of in other observatories as well. The nice thing is that if we're just considering the globular cluster populations, we find that they need to be completed down to at least the peak of the globular cluster luminosity function. Ideally, if you can go lower, you have more tracers, so you have a better estimate. But what's quite interesting is that we do not need to distinguish them by color. So a lot of studies focus on, oh, well, okay, what the blue globular clusters do, what the red globular clusters do. For these masses, as these galaxies are creating so many globular clusters that it doesn't matter their color. They're creating both metal poor and metal rich. So you just do your analysis with whatever sample you have. By doing the analysis on the stars and the globular clusters, if there's also existing X-ray data on mass models from gravitational lensing, then we can place more constraints on the total mass estimates coming from those models. And if you want to sort of dream widely and think that with the combination of all of these methods, we will eventually be able to constrain the nature of dark matter, we need to do this for a large number of galaxies. So all of the studies that I showed at the beginning are very exciting, but they just focus on one system at a time. So we need to do this systematically for a large number of galaxies. And yeah, future surveys seem to be able to give us these number of galaxies. So it would just be a matter of reducing all that data. Yeah, it's a lot of work. So it's very exciting because going forward, there's lots of observatories that can give us sort of that data, and it's just a matter of like find the time. So thank you for your interest, and if you have any more questions, I'd be happy to hear them.
Ron.
Oh, yeah, I'm Roland. That was really interesting. Thanks very much. I'm also a simulator, so I'm sort of stepping out of my comfort zone a little bit. My sort of understanding is that the advantage of using X-rays to map the mass profiles of clusters is that clusters are a lot brighter in X-rays. Right? ICL is difficult to see because it's so faint. But see, X-rays only really allow you to look in the middle of clusters rather than the outskirts. Where do globular clusters lie on that? You know, are they easier to observe in clusters than ICL? Oh.
So I think I think, so the nice thing of globular clusters is that they're very bright and they're very compact. So they're point sources. It depends a bit on the distance at which your galaxy cluster is sitting, I guess. There's gonna be a point where you just don't see them. But they are so bright that you just sort of see them. So for example, the sample that I showed at the beginning for 4 nights, they're capable of measuring or finding globular clusters up to like 40% within R200 in 4 nights. So that's a substantial amount of size or region within the halo that you're probing. The nice thing of globulars is that you can probe them all the way within the VCG. So if you were to use them to probe the dark matter mass profile, you would be looking at different regions, like at different radii regions. And sort of ideally stacking them all together, you might have a complete picture. I think they're compatible. I don't think like one is going to substitute the other, but it might help you probe the inner part of the halo, which is where, like, for different dark matter models, there seems to be more of a disagreement. So
Yeah, I suppose you were sort of saying that looking at the diffuse light is good for going further out, but then like the clusters keep
Might
this
be.
detail in there.
yeah.
Right, thank you.
Right.
Hi, Mike Hudson. So if you go back 2 slides, I think, maybe one or two, no, actually 1 slide, sorry. So, and it's a general question. When you talk about stars, is that specifically the ICL that you separated off galaxies and the ICL, or is it all the stars? The stars in well-identified galaxies plus the ICL?
So for these is both. Yeah,
Okay.
it's the galaxies and the ICL.
Okay.
I think while we were doing this, we just considered the ICL. So the idea was for these was to say, if you just have observations where removing galaxies is not always as easy, what would you see? Rather than just looking at what is the distribution of the ICL.
So a lot of the stars will be just the locations of the galaxies themselves.
Yes.
Then. All right.
And that's true for, I mean, that's true for the globular clusters as well, right? Because they're centering galaxies.
Most of them. Yeah. We can do this with Wednesday.
Yeah.
Imagine that.
Yeah. I mean, you could repeat the entire analysis just looking at everything that's not bound to galaxies. The problem is that you would say that's sort of fairly easy to define for simulations, not so easy for observations. There are many different ways in which people distinguish between these components. So we just decided to go for kind of the more general definition, I guess.
So Dinesh again. So, I guess I'm just trying to understand this from observational point of view, what sort of data we are using. Is it the idea that we use just photometry to identify, I guess, intercluster light and global clusters, or no? Is that the idea?
My idea with the project at the beginning was to say, if I were to take an image of my simulation, what would it look like? That's why I sort of spent a while at the beginning. How do you generate these mock images? So these mock images are just the projection on
Hey,
2
you guys
axes.
let Marta speak.
So these are just the projection over 2 axes of your spatial distribution, yeah, of the stars.
I actually I have a question related to
Yeah.
that, because my understanding of the plot you showed where you were, it's just a few slides back where you were showing that the GCs trace the dark matter better in the inner part,
Yeah.
and the stars trace the dark matter better in the outer region. And I was just wondering if you could comment on the implications of what that means for dark matter tracers currently in use, because it seems like this is kind of bad news for observers, because it's kind of like the opposite of what's easy to observe, you know, like.
Well, so,
the-
yeah, so that's a good question. So what we're seeing that kind of, for example, here in the outskirts, we're seeing, at least from simulations, stars would be better, right? But when you take into account observational constraints, the fact that like large area of deep stellar photometry is difficult to do consistently, then these data point might move upward, right? Like there's just so much that I can do with the mock images list per se when I'm doing these analysis. So although kind of the underlying data, like the underlying stellar data might be closer to the matter than globulars, when you take into account these observational constraints, globulars might just be easier to observe. And so you would just have to be satisfied with this data point because you cannot attain this.
And
One final.
Yeah.
Can you go back to the contour image, the mathematics of it again? So when you identify which two contours to compare the distance with, you mentioned it before, like you go by, how do you identify which two are the?
So what I'm doing, if you don't mind, I'll just draw. Sometimes it's easier. Okay, so let's say this is our matter. So your diametric distribution is gonna have some structure. That's right. Yeah. So what I'm doing is when I'm identifying these contours, I'm identifying them by saying, I want to join all the pixels that have the same density as the radial profile at a given distance, right? That gives me several contours within the image. I take the longest one. And then when I'm making the comparison, I want to compare the contours that are drawn at the same distance. Or the contours that are drawn for the corresponding densities at the same distance in the radial profile. Does that sentence make sense?
Some kind of an average distance between this contour and the left matches one on the right.
No, you take the entire contour. So the modified Hausdorff distance is a summation over all the points of the contour. So you don't average the contour to a value. You're measuring what's the average distance between the X and the Y of two different contours. It's just that the contours that you're choosing correspond to densities of a given radii.
Okay,
So if the two distributions were to be spherical, the two contours would be drawn at the same radial distance from your center.
So I'm saying that you have the left one, you
Yeah.
have the distance associated with it, so like
Yeah.
distance, all of them. And then on right hand, you have two contours.
Yeah, so here you have a contour that has a list of X position or XY, and here you have another list of XY. And so the modified Hausdorff distance, what does is it measures the average distance between your XY here and your XY here.
And then you do that for the other one as well, and see.
You only do it for one contour. So one pair of contours per image at each radial distance.
So that's what, how do you know which one on the right you pick the one?
The longest one. That's part of the
The
trick.
longest.
Yeah, so you need to, so here, if you have several of them, you need to choose something, right? So I chose the longest one as a representative of this is the dominant structure within your galaxy. And that's the problem that arises in the previous halo where, where you're just not seeing the same thing in both cases. So the distance that you would find, the metric is just wrong.
one more, quick one.
I'm gonna be
Some
here until
people
4.
Created the room.
We've already, I think with
Yeah.
timetable, we can have a chat later.
Cool, yeah. All right, let's thank Marta.
Oh, there's a question waiting online.
Sorry, I was supposed to be paying attention, but McNamara has a question. We're done. Do you want to let him go or do you want to?
All right, you guys
One
can
more question,
disperse.
yeah.
I'll be in later.
All right.
Sorry
Well,
for keeping
hang
you.
on. I've got to turn my sound back on because I had it muted. All right. There's echo. Go ahead, Brian.
Oh, I was gonna, okay, well, okay, I was gonna let everybody go because I'm sure everybody's hungry. So I have a question about. Okay, I have a question about something you said early on about, globular clusters and stars tracking the mass better than X-rays, and that surprised me because to the extent that the hot atmospheres are in hydrostatic equilibrium, and there's very strong evidence that they by definition trace the mass. So can you elaborate on that? Oop, I think we're gone.
Okay, so
Boring.
I think you need to close.
Hang on.
Did I not come through?
I think maybe Brian, you can email Marta that question.
Yeah, that's fine.
Sorry, I'll just reply later on.
That's
Yeah,
fine.
no worries. All right,
Sorry.
take care.
Sorry, Brian. I'll try to email you the answer in a second.
Yeah, no